Okay, I think we're recording. Yeah, so today we're going to continue our discussion of MRI. And so we're going to start off by reviewing sort of what we did on RF excitation a little bit. And then we'll start talking about transverse and longitudinal relaxation, sort of what happens to the MRI signal once you've excited it. We'll talk a little bit about the Bloch equation, introduce it. That's the governing equation for MRI in terms of what happens with the spin dynamics. And then we're going to sort of try to start motivating how do we actually make images with MRI. And so we'll review a little bit of K-space. For those who just, it's always good to review that. And then we'll start talking about how do we use the gradients to do what's called encoding. And so that's sort of the next step in the process that we're going to be looking at today is encoding. And then hopefully if there's time, we'll just touch upon the MRI signal equation, which is sort of the equation that shows us that if we do all this right, then the MRI signal is just the Fourier transform of our object. Okay, so we can get to that point. Then if we know we can take a Fourier transform of an object, then we know we can always go backwards and reconstruct the object by taking the inverse Fourier transform. So that's our goal for today. Let me move this out of the way. Okay, that's better. So last time we talked about the four main steps of what's needed for MRI. And so the first thing we talked about, remember, was the big magnet, and that was polarization. So that's the polarization is the act of creating some net magnetization. Without any applied magnetic field, there would be zero net magnetization, right? Because there's no preferred direction for the spins to be. So we need some external magnetic field. It can be something as weak as the Earth's magnetic field. Right now, your spins are slightly polarized in your body. So we actually could do MRI with the Earth's field, but it'd be a very weak signal. And therefore, we want these really big magnets to sort of create enough polarization that we can sort of get a signal that is usable. The next thing we talked about, and we'll review a little bit today, is excitation. So it's taking that polarization. Oh, let me turn on my camera so that people. In MRI, we use our hands a lot rather than spin. So if you can't see, then it's going to be sort of meaningless. So we've created this net polarization, right? And the excitation is taking that away from the where it's sort of equilibrium point and giving it some energy, so it excites it away, and then it's going to this magnetization is going to process around. Okay. And it turns out that that procession is really important because this now creates a time-varying magnetic field. Okay, whereas if it's just here, it's a magnetic field and we could detect it, but it's not time-varying, so it's a lot harder to detect. Okay, so it turns out anytime you have a time-varying magnetic field, then that means you can just put a wire out here and listen and see what that time-varying magnetic field is, right? Through Faraday's law, any dB dt is going to cause some electric field in some pickup coil. So that's the basic principle why we want to sort of excite, so we can sort of have this time-varying magnetic field. Right? So we'll recap a little bit about excitation today and do a couple exercises just so you sort of see some of the practical calculations that MR physicists do when we try to figure out how to excite spins. Then in the second half of today, hopefully we will get to encoding. So that's the job of the gradients. Okay, and so those are remember there's three gradients: X gradient, Y gradient, and Z gradient. And those three gradients have a very important job. Those are a lot what allows us to do MRI. So with just the first two steps, polarization, excitation, you can do NMR. So those of you who have chemistry backgrounds know that NMR, nuclear magnetic resonance, is a very important tool for chemistry. And so that was done for many, many years. Since, say, the late 40s to the early 70s, that was all that was done, NMR, okay? So using chemistry labs. So it wasn't until the early 70s when Paul Lauterbur had the insight, oh, what if you add these gradients? Then you can actually make an image, all right? So gradients are going to be very important for making the image, and the process, the job that the gradients do is something called encoding. They're just trying to encode the information into the MR signal. And then the last step is also important, which is the RF coil. We've talked about the RF coil putting energy in. Now the RF coil has another important goal, is that it also has to receive the energy coming out of the spins. Okay. And what we're going to see is that that is actually an integration process. The coil basically sees all the spins within its sensitivity area. So you can think about it as integrating the contributions from all those spins. And so instead of doing like an integral in MATLAB, the coil is essentially doing an integral for you. All right. And so in general, you see the RF coil is used twice. It's used for transmit and receive. So you could use the same coil for both. You could transmit, okay, and then and that's with a lot of high power, and then you would switch into the receive network, and that same coil could be used to receive the signal. So that is sometimes used, but what's more commonly used these days is you'll transmit with one coil and then receive with an array of smaller coils. Okay, so you'll see both coils that are both transmit and receive coils, but you also see a transmit coil that can just be used in transmit, and sometimes it's transmit only, and then you'll have receive only coils. All right. So that's just to recap where we are and sort of give you a roadmap of where we're headed in the next lecture or two. Okay, so remember what we talked about is spins always process around the magnetic field. Okay, and remember they process at a longer frequency, omega equals gamma B0, right? Or F equals let's see, gamma over 2 pi B0, right? Okay, so for example, so a useful thing to remember for protons is that basically the Larmor frequency, the gamma over 2 pi that we use throughout the course, you know, it's about 4257 hertz per Gauss. Okay, so for every Gauss of magnetic field, that means the spins are going to go around about 4,000 times a second. And so sometimes for problems, we'll just assume that it's about 4,000, so it's easier to do the calculations in class, all right? But it's 4257 or 4258, depends. People use slightly different numbers. So for example, in your pre-lecture quiz, you saw it asked you what is the resonant frequency at the Earth's field, right? When you're at the Earth's field is half a Gauss, right? Approximately in San Diego. Has anyone gone and measured the field yet? Anybody? No? Okay, so for your homework, oh, you did, okay, great. Did at home. Okay, so, yeah, so 0.42 Gauss you found, okay. So there you go. So if we take 4,000 and multiply by half, that gives you about 2,000. So that means that right now your protons are processing about 2,000 times per second as you sit here. Okay. So remember, so right now your protons, you see the first part of the movie, there's that, so there's a net magnetization, right? So you have a net magnetization right now in your bodies, right, through the Earth's magnetic field. But there's also, because of sort of random thermal energy, you know, you don't have, not all the spins are pointing in that direction. It's just the net is pointing that direction. You actually have all these spins that are shown here pointing in all different directions, and they're all processing around at 2,000 cycles per second. And so the idea is we're going to take that whole ball of magnetization and sort of try to excite it away. Okay. So even in those pictures, you see this big push ball. In general, we're just worried about the net magnetization. Right? So if you watch this movie, which we saw last time, hopefully it runs. So the idea is we use a little tiny B1 field to sort of start processing the magnetization away. And typically stop when it's about 9 degrees, but you can see in this example, it goes further. And we'll see later in the course, sometimes you might want to excite it all the way 180 degrees, and that has uses. Okay. So even though we'll mostly talk about 90-degree flip excitations, actually all different flip angles are useful. And we'll see later on in the course why that's useful. So remember, the picture of RF excitation is the key that you have to remember is the excitation has to be on resonance. Okay. Essentially the same thing as if you're going to push something heavy on a swing, you've got to push it at the resonant frequency. If you don't, it's going to be very difficult for you to get that large object swinging. So remember, this B1 field we're talking about is really tiny. Okay, it's on the order of the Earth's magnetic field. So we might have this main B0 field, which is, as we saw in the pre-lecture, it's about 60,000 times the Earth's field, right? So you have this really strong field that wants the magnetization to stay there. And you have this little itty bitty field that's trying to get the magnetization to go away from there. And the only chance it has of doing that is if it's out in resonance. So over time, it can sort of encourage the spin to go away from its equilibrium. And so that's what this we saw last time. We'll show it again. It's a very useful picture. So the spin basically follows the applied field down to, in this case, the transverse plane. And similar to if you try to get something swinging and you're hitting it with the wrong resonance, the same thing occurs if you are off resonance with your B1 field. You perturb it a little bit, but you never quite get it off where it wants to be. It really wants to just be aligned with the main B0 field. So if you're not right on, you're never going to get it off too far away from that where it wants to be. Okay. So we talked a little bit about rotating frame of reference, which will also be useful when we think about how do we do the encoding. And essentially, for most of this course, unless you're told otherwise, we're always in the rotating frame of reference. Okay. Because otherwise it's just too hard to think about. You don't want to think about spins going around 127 million times a second. You don't really care about that overall procession. What we're really going to care about is the relative phase between spins. Okay, so that's the rotating frame of reference. Essentially, like if you're on a merry-go-round and you have different people on the merry-go-round, you don't really, at some point, it's just a relative relationship among the people. Let's say people are walking on the merry-go-round. You just care where they are on the merry-go-round. You don't really care that the merry-go-round is going around, all right? Just like right now, we're all sitting on planet Earth, which is going around pretty fast. But for our everyday life, it doesn't really matter. We just care about the relative motion in that frame of reference. So what that means is that instead of having to worry about the magnetization spiraling down, if you are going around the field that's being applied around resonance, then it just looks like the magnetization is just coming right down towards you. Okay. And so that's shown here where we're applying the field. The magnetization is here and we're applying this field here. And the magnetization wants to go clockwise around this field. So it's just going to come down and go like that. Okay. So that's what's shown in this movie here. Okay, with some music there, right? Okay, so that's basically, so in the rotating frame of reference, it's just a simple flip angle. We're just basically taking that magnetization and flipping it down away from the vertical axis. Okay. So that we end up with our first equation that we're going to play around a little bit, which is we're going to find a flip angle. So flip angle is one of those key. We're going to see that to prescribe an MR exam, there's probably about 5 to 10 really key parameters we need to think about, and one of those is flip angle. Okay, so this is the first parameter we're introducing you to. Flip angle is essentially what's the angle that you move this away. So this would be flip angle 0, 90, 180, and so on and so forth. Okay. So flip angle is essentially, we know that if we apply some magnetic field, B1, the alarm frequency in radians per second is just omega1 equals gamma times B1. Okay. And that's also just to point out, when we talk about the main field, we'll always call it B0. And then anytime you see B1, that's the RF field. Okay, so that's good to know. It's not just random. We call it B1. Everywhere in MR, you'll see it's called B1. All right. So we call gamma 1, omega 1, that is the radial frequency at which it's processing away. Okay. So we simply integrate omega 1. Also, just to point out, when we talk about the main field, we'll always call it B0 or B1. All right. Can you mute yourself, please, in the audience? A little delay there. Great, thank you. Okay. So we just simply integrate that frequency over time, and that gives us our flip angle. All right, so we're going to do a couple exercises together to look at that. So here's the most basic thing we can do. All right, so assume that this is a function of time. Okay, and at time equals 0, we turn on this field. So this is the most basic MR experiment you could do. All right, and this is the B1 field. So B1 is a function of time. And you essentially turn it on with some value B1, let's say. Okay, so it's got some amplitude. And in this case, it's turned on for 400 microseconds. Can you all read that? Okay. Right. If not, let me know. I'll try to write better, but handwriting on an iPad is not my greatest strength. So basically, now what we can say is, let's say I had a pulse that I had on for 400 microseconds, which is a very short pulse, and I want to get the flip angle of pi over 2. Okay. So then the question is simply, what should be the size of my RF pulse? So we know that theta is just equal to omega 1 tau d tau. So it's the integral of that. That's just equal to gamma b1 of tau d tau, right? But since b1 is constant, yes, question.
So B naught is the base magnetic coil and B1 is the RF pulse?
Yes, that's right. So B0 is always what we call our main magnetic field, which is the one that's very strong typically. Yeah. Okay. So we can write this as gamma times B1 times the length of our, because we're assuming B1 is constant in this case, so it's just the area under our curve. Okay. So in general, you can always say that theta is equal to gamma times the area of the pulse. Okay. So anytime you're looking at something, it's just gamma times the area of the pulse. Right. So then what we can say is we want theta to equal pi over 2, right? So now we can solve for B1. B1 is just equal to pi over 2, and we divide by gamma, and we divide by 1 over t. Okay. So gamma is just 2 pi times 4257 hertz per Gauss. Okay, and then the t was just 400 times 10 to the minus 6. Okay. So if you plug that all in, you get that this pulse is 0.1468 Gauss. That's the amplitude you need. Right. So we're seeing that that's on the order of the Earth's magnetic field. It's about a third, or a little less than a third of the Earth's magnetic field. Okay, so these are very low amplitude pulses that we use. Okay. So the key then, once again, is flip angle is also equal to gamma times the area of the B1 pulse. Okay, any questions on that before we move on? So this is a sort of question that then we're going to use this to review a little bit of Fourier transforms, because we're going to start using Fourier transforms a little more. And so this is a good problem for sort of reviewing some of the key concepts of Fourier transforms. So I think this was a homework problem maybe 5 years ago or something. So you might expect a similar homework problem, later on in the course. Maybe even this week. I haven't made up the homework yet, so something like this. So here we consider an RF pulse of the form A times sinc t over t. Okay. So first of all, I always recommend drawing out what that is. Right? So it's going to be a sinc pulse, right? And it's going to have amplitude of A. Okay. And then this t is 250 microseconds. Okay. Because that's the first zero of the sinc, right? Because when t over t equals 1, then t must equal big T, right? So that's just the first zero, right? And you're given, so now you're saying, I want my flip angle to equal pi over 4. Okay, I know that's just going to be a gamma times the area of my pulse. Okay, so now it's pretty straightforward. I just have to integrate my sinc function, right? So let's assume that you don't really feel like integrating a sinc function right now. So what could you do to sort of save some time and not have to integrate a sinc function? Yes.
If I keep the Fourier transform,
Yes, right. So the Fourier, so one key thing is that the area of any function is just the value of this Fourier transform at 0 frequency. So that's a really useful thing to remember. And we'll touch upon a little bit when we talk about k-space. So anytime you're looking at areas in one domain, it's always equal to the value of its transform or image transform located at 0 in that other domain. Right? So then what we know is we can just say, okay, well, if that's the case, I can just say A sync T over T. Okay, and I want a Fourier transform of it, right? And I'm going to apply the scaling theorem, right? So I'm just going to get A times T times rect of F T. Okay, so that's applying the scaling theorem. If you haven't seen that, or this we'll be using the scaling theorem probably the most of any of the theorems in Fourier transform. So if you need more information on that, let me know, but there are the supplementary lectures and you can take a look at those. Okay. So at f equals 0, this just goes to 1, right? At f equals 0. Right? Because the rect function is 1 within minus a half to a half. So if I put in f equals 0, that's just going to be 1. So we know that, so the nice thing is the area of this, the area is just A times T. Okay, and that's a useful thing to realize about the sinc function, because anytime you see a sinc function, you just know, okay, the area of that sinc function is just this amplitude times its first 0, which sort of makes sense if you look at what the sinc function looks like. You know, its width is this width, right? This is T, right? That width is T, right? So about, but you know, it's sort of coming down. So if you think about what's the effective width of that, it's probably about T, right? Okay. So now we're set. We can just say that pi over 4 equals gamma times A times T, and that's equal to 2 pi 4257 hertz per Gauss times A, which we're trying to solve for, times T, which is 250 times 10 to the minus 6 seconds. So we can cancel out the pi's, and then we can divide by the 2, and we get 1/8 equals, oh, and then it says assume that it's 4,000 hertz per Gauss. So let's make our lives easy. That's 4,000. So we have 4 times 10 to the 3 times 2, what is it? 250 times 10 to the minus 6, which equals 1,000 times 10 to the minus 3, which equals 1, right? Times A, right? It's all times A, right? So A is just equal to 1/8 of the Gauss. Yes, question.
Pi over y?
Pi over 4. Yeah, because theta is equal to 45 degrees, right? So that's about 0.125 Gauss. And so in this case, the closest answer would be 0.12 Gauss. Okay. So it's a little bit of algebra, but and most problems in this course, that's the sort of level of algebra you'll need. So it's not too bad, but it's just applying the right concepts. In this case, the key is remembering flip angle is just going to be gamma times the area of the pulse. The trick might be then to find what's the area of the pulse. Okay. All right, so that's sort of the first sort of a practical problem we've got with it. So this is the type of calculation that goes on in MR scanners every day. It's probably being done thousands of times right now. You know, every time someone enters in a flip angle, the program has to calculate what B1 amplitude to use, and so that's being done right now. Okay, in hospitals all over the world. Okay, so we're going to revisit a little about free procession now, okay, because we want to understand. So the next step we're going to look at is what happens when I tip something away. Okay, we said it processes around, right? So we have this basic picture that an ionization that's tipped away will process around the main field. But now we want to have a little more mathematical description of what is procession. How do we describe procession? Okay, because this is going to lead up to what's called the Bloch equation. So remember, Felix Bloch is one of the discoverers of NMR and got the Nobel Prize for the discovery along with Edward Purcell, I think in the 50s, right? And so he's the one who sort of came up with the first equations describing how sort of NMR phenomenon works. So as we recall from last lecture, or you may recall that the governing dynamic equation is that dm dt is equal to m cross gamma b. Okay, where b is the magnetic field. Okay, and m is the magnetization. Okay, so it's m cross b. So the cross product is going to point this way. Okay, and that means, and it's going to be perpendicular to this. So it's always going to be perpendicular to the tip of m. And so it's just going to try to cause m to go around in a circle. So that's the physical picture, right? So that the dm is always going to be perpendicular. It's sort of tangential to the m, but that's going to go around in a circle. So let's write that down. So you may or may not remember that you can write a cross product as a determinant, okay? And you may remember what a determinant is, but if you don't, this is the expression. So the second line here is just the determinant. So you take ijk, you write out the coordinates of mx, my, mz, and bx, by, bz, and you multiply that by gamma. And then you remember how to do a determinant, and it gives you this equation here. All right. So that's all that is. And then the next step is we say, well, what we'd really like to do is write this. So we have each of these dmx, dmy, dmz terms written in these terms as products of b terms and m terms. And so what we'd like to do is we have mx, my, mz on this side. So we'd like to isolate the mx, my, z on this side as well. So we can come up with a nice equation of motion, right? And so it turns out that if you go through the algebra, you can rewrite this in this nice form where it's just gamma times this matrix, okay? You see these are all off-diagonal terms, okay? So anytime we're dealing with procession, we're always dealing with off-diagonal terms. And then, my daughter trying to call me. I should silence that. Okay. And then what we'll see later on is these diagonal terms that are zeroed out, we'll fill those in later in the lecture. Those are going to be the relaxation terms, right, for the Bloch equation. So at the end of the day, we can rewrite this. And what we're going to do is we're going to look at the solution to this, okay? And the first thing we're going to do is look at the solution when we only have a BZ term. All right, so we're going to zero out these bx and by terms. So before we do that, I want to review a little bit about phasors. Dr. McVeigh talked about this a little bit, but phasors are like super important for MR. It's like if you understand phasors, you'll understand MR, and if you don't, MR is going to be really difficult. Okay, so up to now, maybe phasors are just some of this sort of like abstract concept. But in MR, phasors are actually they are physical quantities. The phasor is essentially the position of the spin. It's the phase of the spin, okay? So the more we can sort of be comfortable working phasors, the easier time we're gonna have with MR. And then if you understand MR, that's gonna actually let you understand Fourier transforms even better, because it's actually a physical implementation of phasors and Fourier transform. So remember, e to the j theta is just cosine theta plus j sine theta. That's just Euler's theorem. Right? And so the key though is to remember that what is this theta term? So we're going to be looking at terms e to the j theta like all over the course, okay? When we're talking about MR. So that theta is going to be turned out to be super important. So we want to understand what that theta is. And so theta is just the angle of the phasor. So you just have to know that like theta equals 0 looks like that. Theta minus pi over 2 is that. Theta of pi is that. And theta of pi over 2 is that. Okay? It's just the angle reference to the x-axis. Right. So pretty simple, but it's one of the key things you need to keep in mind. Okay, so what we're going to do is we're going to look at procession when there's only, so we're going to assume this is the picture. We have our B0 field, we're going to apply a B1 field to excite the magnetization, and then we're going to turn the B1 field off. Okay, so now the only field left is the B0 field. Okay, so we have this B0 field here that's still on, and the B1 field is off. And so now the procession, we're going to describe procession. Okay. So now we only have these B0 terms here. Okay. All the other terms are gone. And so you can sort of see one thing that's pretty obvious is dmz dt is just going to equal 0. Right. So that term just comes out. Right. So that means that free procession in the absence of anything else, the z component of the magnetization is not going to change. Right? Okay, so I've tipped it away. It's just going to turn in a circle. So that z component never changes because it's just tracing a flat circle in space. So I only have to worry about the x and y components. And this is here is where the phasor notation becomes very useful. We're going to define our complex vector m as mx plus j my. So we can keep track of what the magnetization is with just one number. Okay. Instead of having to track mx and my everywhere, we can just say it's just going to be equal to mx plus j my. And it turns out if you do that and you plug into this equation, you can rewrite the equation as dm dt equals minus j gamma b naught m, where this m is that complex number. And this is just a first order differential equation, right? The simplest equation you could think of, right? And so it clearly has a solution of m of t equals m sub 0 times e to the minus j gamma b naught t, right? Okay. So basically every first order differential equation is just an exponential, right? Because an exponential has an exponential as its derivative. So this is the key finding that, and then we can rewrite this gamma omega naught equals gamma b naught. Okay, so we can also write that as m sub 0 e to the minus j omega naught of t. Okay, so now this is a phasor that has a frequency of omega naught of t. Omega naught, and it's varying with time. So if we look at the mxy plane, if this is x and this is y, it's just a phasor in that plane. Okay, that's just spinning around at a frequency of omega naught. There's a minus sign there. So what does that mean? Which way does it rotate with time? Does it go clockwise or counterclockwise with time? Any thoughts on that? So that's important. That'll be important for the rest of the course. So it's good to sort of get that clear now. So I give you something e to the minus j omega naught t, and I'm saying that's my time varying magnetization. Is the magnetization, and I look down on the xy plane, is it going clockwise or is it going counterclockwise? Go ahead. Counterclockwise. Okay. Good. So one vote for counterclockwise. Any other suggestions? Okay. So why would you say it's going counterclockwise? Okay, that's fine. Learned from another class. Okay, great. Ooh, there's another hand up there. Tentative. Maybe. Okay. Well, was there a hand back there? Is that a hand or? Oh, trying to use your hands. Okay. Yes. Yeah. Yeah.
So I think there's a step in the homework where you do make the negative and the helix spin.
Okay.
I don't know if I did the homework right.
Okay. Well, let's go over this because this might help with the homework then. Okay. So remember, we're always looking at things of the form e to the j theta, right? So the simplest thing is anytime you get confused in general in research is it's always useful to write things down in a simpler term so you isolate what's really important, right? So this solution just has the form e to the j theta, right? And what is theta? Theta is equal minus omega naught t, right? So that's all it's saying. It's just saying the angle of your phasor is minus omega naught t, right? So as a function of time, as time goes, if I plot it as a function of time, that angle is just becoming more negative, right? So if I'm here, and this is theta equals 0, then it's going to, well, the problem is if it's counterclockwise for me, it's clockwise for you. So it's basically, you have to, this is basically, so this is x equals 0, right? So negative theta is going to go this way, right? So it's going to go clockwise, right? So the rotation is going to go like that. Okay, so the sign, it turns out the sign is going to be important because whether it goes relatively one way or the other way is the difference between positive and negative frequencies. Okay, so if that is a negative, that means that rotation is always this way. Okay, the angle is becoming more negative with time. If it was positive, it would go the other way. Right? Okay, any other questions? Everyone okay with that? It's a small point, but it's actually useful to sort of make sure you're sure about that. Okay.
Professor,
Yes.
you probably have turned on blurry the background, so it's kind of hard for us to see you pencil.
Great point. Let me see if I can change that right now.
Mm-hmm.
Backgrounds and filters. There we go. Okay, is that better?
Yes.
Okay, thanks for pointing that out.
No problem.
Question in the back? Yes. Yeah. So the answer is clockwise. Okay, the next thing we're going to talk about is we're going to get into relaxation, which is, we just said that it's just going to process forever, right? But nothing lasts forever, right? I mean, something is going to make this magnetization go back to here, right? Otherwise, you'd have a perpetual motion machine, and you wouldn't have to, have any energy to keep this going, all right? So that process of that magnetization decaying away is what's called free induction decay, or it's also, if you hear the term FID, that's what it is. And so the idea is, in here, the magnetization is in equilibrium. We apply an RF pulse. That RF pulse tips it away. So the magnetization is transverse now. And then it processes around, but as it's processing, you see it's getting smaller and smaller in amplitude. So now we want to look at that, because that's one of the key, and this is one of the key things with MR, is you're always battling time. Okay, so time is a really important element in MR, because you only have that signal for a certain amount of time. And if you don't get the signal before it dies, you have nothing. Okay. So time is going to be very important for us to think about in MR. Okay, so the free induction decay is basically just going to look like a decaying exponential. And what we want to do now is give some, we're going to do two facets of this. Today, we're just going to give you a very quick overview of relaxation. Later on in the course, we're going to come back and look at the sort of detailed mechanisms that give rise to relaxation, and so how you might manipulate it. Today, we're just sort of just giving you a high level view of it. So the important thing is we're going to think about both longitudinal. So when we say longitudinal, that's the M sub Z component, and transverse, that's the MXY component. Right? So we're going to think about those two things separately. So T1 is what's known as a spin lattice time constant, and that governs the return to equilibrium of M sub Z. So anywhere you see M sub Z, you know that's relating. Anywhere you see T1, you know that's related to M sub Z. Okay. And then the other time constant we have is T2, which is known as the spin-spin time constant, and that governs the return to equilibrium of MXY. Okay, so T1 governs longitudinal relaxation. T2 governs transverse relaxation. Okay, so it's good to keep those two separate in your mind. So let's look at longitudinal relaxation first. The governing equation for longitudinal relaxation is just this first order differential equation. It's dm sub z dt equals minus mz minus m naught. So this is how far away you are from equilibrium, right? So if you're already at m naught, then that's going to be 0, right? So nothing's going to change. You're already back at equilibrium. But if you're anywhere away from equilibrium, this term is going to drive you back towards equilibrium. Okay. So for example, let's say m sub z is equal to 0. Then I'm going to have minus times a minus. So that's going to be a plus, right? So if I have this magnetization here and I flip 90 degrees, what's m sub z now at this point in time? 0, right? So that means that the dmzz is going to be positive. It's trying to push the magnetization up, right? So it turns out that, so for example, after a 90-degree flip angle, the solution to this equation would be m sub z of t equals m naught times 1 minus e to the minus t over t1. So it's just exponential recovery to m sub z, right? So in this case, I start up at 0, and it's just exponentially recovering to m sub naught. All right. And the reason that's important, which we'll see later in the course, is because different tissues have different T1s. All right, and so one of the bases of contrast in MR is T1 contrast. Right, and we'll see how that can be used in different ways later on in the course. But for now, I just want you to know that the reason we're talking about T1 is because if T1 was the same for everything, we wouldn't really care, right? Because it wouldn't give us contrast. But because T1 varies according to tissues and tells us something about the tissue, we can use that as a way of contrasting different types of tissue. We also have transverse relaxation. So now we have an even simpler form. It's just dmxy dt equals minus mxy t over 2. Okay. So this is always going to be negative, right? Because mxy is just sort of the magnitude of the magnetization that we have. So this is always going to be driving the magnetization to get smaller and smaller and smaller. And that's consistent with our picture that this procession can't last forever, right? This stuff going around transverse, it's got to die away at some point. At some point, it's not going to be there anymore. Okay. And it turns out that we can always show that T2 is less than T1. We'll talk about that a little later, but for now, the picture we want to have in mind is the magnetization. Let's say we're in the rotating frame. It starts off here and then just decays down to some smaller value. And that's the free induction decay. So you have mxy equals m naught e to the minus t over t2. Okay, so just an exponential decay with a time constant of t2. And once again, the reason we care about T2 is because different tissues have different T2. Okay, and we're going to take advantage of that later in the course. We're going to show how we can manipulate our MRI pulse sequence to take advantage and highlight some of these contrasts in these different values. One of the physical mechanisms behind that is the spins. You know, we sort of think about one spin, but in any given volume, you have many, many spins, right? You have millions of spins, right? So it's really, the T2 is really the fact that the spins are not always going around at the same rate. And so that's going to lead to dephasing, and that's what leads to this decay. We'll talk about that more later in the course. Today, we're just going to talk about how we can put all these things together. And this is the famous Bloch equation, named after Felix Bloch. And it just says dm dt is equal to m cross gamma b. That's the procession we talked about. So that's the part that gives rise to the procession. At the same time, we're going to have mxy decaying away with transverse relaxation. And we're going to have m sub z growing back with T1 relaxation. All right, so three things are going at the same time. There's procession, there's decay in the transverse plane, and there's growth in the longitudinal plane. Okay. And even though it's a very simple equation, it turns out that this, if you understand this equation, it gives rise, it can be used in many different ways to give rise to many interesting properties. So we can rewrite this equation now. Before we had the minus gamma b naught and the gamma b naught terms. Now we're just going to add these diagonal terms, minus 1 over T2 here for the x and y components, and minus 1 over T1 for the m sub z component. And plus we have this m naught over T1 term for the z component, because that's sort of telling us where we're trying to go back to, right? The mxy components are going back to 0, so these just have 0, whereas the m sub z component is going to something related to m sub naught. Okay. So it turns out that this is the equation we saw earlier, just written in a slightly different format, and this is the general solution for that equation. Okay. So you can sort of see this term here is where we're trying to go back to. It's always trying to go back to m sub 0. That's the equilibrium magnetization. And if we're already at m sub 0, this term goes away. And if we're not at 0, this term is going to have some exponential growth. Right. So there's two main things that we'll talk about in this class. And we'll introduce them today, but we'll also revisit them later. One is saturation recovery, and the other is inversion recovery. Okay. Saturation recovery is what happens when you apply 90-degree flip angle. So you start off at m sub z equals 0. So saturation recovery just looks like that. Okay. Inversion recovery is when you start off, you tip the magnetization all the way 180 degrees, so it starts off at minus m naught. Okay. And then it's still going to recover, and then it's going to recover like that. So those are the two most important types of recovery that we'll look at in this course.
That would be a flip angle of 180.
Yes, yeah. So inversion recovery is flip angle of 180 degrees. Okay. And why is that useful? Well, let me just, if you think about this, this curve here, if we start off at minus m naught, to get back to m naught, it has to go across through 0 at some point, right? So it turns out that, let's say there's some tissue that you want to erase, you don't want to see it, right? You can always time your acquisition so you acquire the data right when that signal is crossing 0. And that's where inversion recovery is really important. It's sort of a cute thing. You can actually say, for example, you might say, oh, there's all this fat in my image, and I'd really like to see, what's there when I take away the fat, right? Well, you don't have to, you could just sort of maybe try applying some chemicals and, cause damage to your object and try to get the fat away, right? But in general, like if you're imaging someone, you might care, how much fat do they have in their liver, right? Like fatty liver disease is a really issue. So a key measurement that's going on right now in lots of hospitals now is people are measuring liver fat with MR, okay? And this isn't the only way, but this sort of suggests that, well, one way you can get rid of fat is by just nulling it out. Okay, so that's just to give you a preview of coming attractions. Okay, so we talked a little bit about the transverse component before, and we said that it would just process around, and that was this e to the minus j naught term, e to the minus j omega naught t term. So that's the procession going in a clockwise fashion. Now the solution that we're going to add is it's also going to decay with e to the minus t over t2. So now we have this clockwise rotation, right? This is the x, y, right? So mx, my. So it's going clockwise, right? But now it's also decaying away. So that's the transverse component. And so this picture just shows that we have two things going on at the same time. We have the transverse component dying away, and at the same time, a longitudinal component is growing. So I'll play this movie, and what it's going to show you is sort of show you in real time what's happening. So here you see the transverse component is dying away over here, and that's shown this. And even after this has died away, you're still getting regrowth of the longitudinal component. Okay, so let me play that one more time. So on this side, you're going to see the transverse component. This is the magnitude of the transverse component, and this is the magnitude of the longitudinal component. Okay, so you see the transverse component dies away pretty quickly here. And then even after it's died away, the longitudinal component can still be regrowing. Okay. So that's shown in this picture here. Typically, for most tissues, what it looks like is this transverse component will sort of die away fairly quickly. Okay. And even after it's died away, there's still regrowth of this longitudinal component. So you can think of it as the transverse component is the signal you have to use. It turns out that's the signal that we're going to use in MR, right? And so how quickly that dies away tells you how fast you have to collect the data, right? If you collect the data after it's all died away, then you get nothing, and your image looks black. Right? So we only have on the order of 100 milliseconds to collect our data. In some cases, we have less than a millisecond to collect our data, so we have to go really fast. The T1 is sort of, that's sort of like how much money you're putting in the bank, right, that you can use next time, right? Because that's the regrowth and magnetization to equilibrium. So there's two things going on. So if you try to come back and do an experiment too soon, you're not going to have enough money in the bank to sort of do your next experiment, in which case your SNR will also be low. So there's these two trade-offs that we're going to have to look at later on, and that's going to govern the design of some MRI pulse sequences. Okay, so that's sort of just a quick view of relaxation, which we'll come back to later in the course. Are there any questions before we move on? Yes. Can you repeat the question? You mean, will it fully be regrown? Yeah, that's a great question. That's up to you. So basically, it's, I mean, I'll use this analogy. I think the best analogy still is like an old-fashioned toilet, right? You know, toilets, like they have water. I mean, hopefully most of you have seen one. You know, there's water in the toilet, right? And then after you flush it, right, you have to wait for time for the water to go back, to full level, right? But you don't have to wait, right? I mean, you could flush it at any point, right? But if you flush it too soon, you know the next flush is not going to be very strong. If you wait 5 seconds, maybe you get a very strong flush, but maybe you're in a rush and you don't want to wait. So maybe what happens if you wait till it's half full? Maybe that's enough. So that actually is going to turn out to be a parameter that you can choose, and we'll talk about how you would choose that, later in the course. So yeah, we don't. In some cases, we might wait for it to grow back fully to M0, but in many cases, you don't wait because you want to go as fast as possible. So you're like, I don't want to wait. Okay, so that's a great question. Anything else? Okay, so just to recap and tell you where we're going, we've talked about polarization, we've talked about excitation and also relaxation. Now we're going to talk about encoding and integration. Right? So remember the MRI gradients. There's an X gradient, a Y gradient, and a Z gradient, and their job is to create non-uniformities in the magnetic field. For this course, we're going to talk about linear gradients. There is research being done in nonlinear gradients, but that's a little more sort of cutting edge research, so we're not going to talk about that. So when we talk about gradients, we're always going to be talking about linear gradients. Okay, and the key is that spins are really, really they're very faithful to the laws of physics. They spin at the local alarm, or at the local, the frequency at which they process is the local alarm frequency. So whatever field they experience, that tells them how fast to spin. So if I have two spins and they experience different fields, they'll also process at different frequencies. Okay. If I change the field that some spin is experiencing, then its frequency will change as I change that field. All right. So that's the property we're going to make use of. And so the key is, instead of just being okay with this uniform field, B0, we're going to add a delta field, delta B. It's still going to be in the Z component. Okay, so that's important. We're always adding something in the Z component, but it can vary with X, Y, and Z. Okay, so that means that by adding this delta B and controlling how it varies across space and in later time, we can exquisitely control the frequency of procession of every spin in your body. Okay. So here's the basic idea that you want to think about. So if I'm here at what we call, and the center of the magnet is what's called isocenter. And typically that's defined as like delta B is equal to 0. Okay, so for the purpose, if I say we're at isocenter, that means that spin has no added field to it. Okay, that's the 0 coordinate. Okay. So spins there are going to process at gamma times B0, right, at isocenter. And they're always going to process at that because we're assuming that's the center. If I go off here in the positive X direction, and now I'm assuming this linear gradient GXX, right? So that's a linear function of X, this is GX times X. The delta BZ I'm adding is GXX, and so spins here, because the field is stronger, they're going to process faster. Right? And then spins here are in the place where it's a negative X, and so GX times X is negative. So gamma B0 minus gamma GXX is going to be a smaller field, so these spins are going to spin more slowly. So that's the key concept. We're going to make spins spin at different frequencies. Okay. And then what we're going to do is we're going to look at the relative phase of the spins. And that's where the E to the J theta comes really important. We have to sort of have this sort of ability to sort of think about, well, what's the phase of the spins going to be? So here's some movies. So here, for example, you're seeing the spins here at isocenter are sort of relatively not moving, right? Because the other thing is we're gonna go to a rotating frame of reference. So the isocenter is where there's no added positive or negative frequency, right? So these spins are just they're at the Longitudinal frequency, so they are spinning at gamma times B0. But now we go to the rotating frame of reference, they're not spinning at all. Okay. And then this, let's say this is X direction. So you can sort of see these spins are going clockwise, right? Reference to this spin, and these spins are going counterclockwise. Okay. So are these spins going faster or are these spins going faster? Can we tell by just the what we talked about in terms of clockwise versus counterclockwise? thoughts on that? So these spins here, they're doing the same thing, but one is in reference to the center column, these spins are going clockwise, right? And these spins here are going counterclockwise, right? So the question is, which spins are going faster in absolute? Yes. Sorry, can you say that louder? Yeah, what I'm saying is these, with reference to these spins in the middle, are these spins processing faster or are these spins processing faster? Yeah, the reference frame is reference to the column of the middle. Yeah, what we said is the spins are always, procession is always clockwise. Yeah, procession is always clockwise. So given that, because we talked about that about 10 minutes ago, right? So procession is always clockwise, right? Because we said it's e to the minus j theta, right? The theta is negative, right? So procession is always clockwise. Then are the spins here processing faster or are these spins processing faster? Yes. Yes, these are the spins that are processing faster, right? So you could, just by looking at this movie, say, okay, the field here must be stronger than the field over here, right? Because procession is clockwise. So if something's going even more clockwise than your reference point, then it must be going faster. Okay. Similarly here, now clearly we've applied a gradient in this direction, right? And if we look here, the spins down here are processing faster than the spins in the middle. Okay. And then these spins are processing equal and opposite direction. And so they're in a lower field. So if this had some delta B added to it, this would have a delta minus B added to it. Okay. And then it turns out that you don't have to just apply gradients in the X and Y direction. You can apply gradients in both directions at the same time, right? And so in this case, it's this diagonal. That's my frame of reference. And now these spins here are slower, and these spins here are faster. Okay, because I can apply both X and Y gradients at the same time. In general, I can apply X, Y, and Z gradients all at the same time. So I can come up with any different spatial variation of the spins. Okay, I think in the interest of time, we're going to skip over this problem today, and we'll come back to that next time. Because I want to sort of just give you a sort of a sense of how the MR works. So remember what we talked about before. We were talking about, this is the laboratory frame where spins are spinning around, right? And then in the rotating frame, then the spin would be stationary. And so this is exactly what we just saw in those movies, that we're going to assume that that center column, those spins don't have any added precession. So they're just, in the rotating frame of reference, they're just solid. Okay. So Erwin Hahn was a very famous physicist at UC Berkeley. I think he just died a couple years ago. He said, there's nothing that nuclear spins will not do for you as long as you treat them as human beings. Okay. That's sort of an interesting quote. And I think what he meant by this quote was basically spins sort of, they act according to certain laws, and you can sort of start thinking like a spin, thinking of them as human beings, then I think when he was doing his experiments, it allowed him to get sort of insight into what the spins would be doing, just imagine what the spins would be doing. And that allowed him to come up with a lot of different innovations over his 50 years of academic career. So when this class was 100% in person, we used to do an exercise where I actually had people come up here and we would do demonstrations, but since it's hybrid, we're just going to sort of do it. We'll do what we did last year, which is sort of a more Zoom-friendly approach to that. So, but you can imagine, like, so in the old days, what we do is I would pick 5 volunteers to come up to the front of the room. Okay, so don't worry, we're not going to do that this year. But imagine you're one of those 5 volunteers. So what I would have you do is I would have you all line up in a row, okay, facing that wall, right? So that's like X equals 0. So that's theta equals 0, that direction there, okay? And so, and all the spins are aligned. at time equals 0, right? So then the next thing I would tell people to do is imagine that you're in a B0 field, and the B0 field is pointing that way. And then I would ask the people to start processing. Okay. So imagine you're standing in this room, and you're all facing that direction. And you start, and I say, at time equals 0, start processing. So what should these people be doing? Which way should they be turning? Should they be turning to their right or to their left? Assuming this is the B0 field. So you can just imagine what. So let's say you face this direction, right? And you're a spin, right? And your spin, this is the transverse plane. So your nose is like where the spin is pointing. And this is the B0 field. So I say process, which way should you turn? Should you turn right or should you turn left? Third, did you say something? Which way would be clockwise? Right, you would turn to the right, right. And so if you were one of these spins and you were in this room doing this experiment and you're in a uniform field, then how should these spins, what should be the coordination of these spins? They should all be going at the same rate, right? They're all experiencing the same field. So that actually turns out to be, the first time people do it, it doesn't always work, but then after time, they all start dancing in the same direction, right? So it's sort of like a dance, right? They're all rotating in the same direction. Now, the next question I would ask is, now imagine you're in a rotating frame of reference, okay? And when I say go, I want you to process. Okay? So imagine you're in this row, you're all facing that direction, and that's theta equals 0. So when I say process, and you're in a rotating frame of reference, what should you do? Sorry, go ahead. Don't do anything. Yeah. So that's always sort of, the class always gets a kick out of that because usually 1 or 2 people will move and the others will not move, and then it's sort of what are you supposed to do? Okay. So that's the key. That basically, if everyone's in the rotating reference, then there's not going to be any relative motion, right? Because you're going to stay at theta equals 0. Now, in the demonstration, we assume that this person is the isocenter. Okay. So the instruction is this person is not going to move at all. Okay, because they're not experiencing any net field. And then we assume that there's a gradient of magnetic field such that there's a plus field here, and a negative field here. Okay. So this person here is going to go clockwise, by say 90 degrees each step. So this is going to go 90 degrees each step. This person here is going to go 180 degrees each step. Just like what we saw, it's going to go more clockwise, right? What we saw in those movies. This person here is going to go counter, 90 degrees clockwise. Let's get rid of these pluses. And this is going to go 90 degrees counterclockwise and 180 degrees counterclockwise. Okay? Because if you're in a stronger field, you're going to be more clockwise rotation than if you're in a weaker part, you're going to have more counterclockwise rotation. So let's just watch this this simulation. So sort of here you can sort of see that both these spins here. Let me see if I can erase what I just drew. Just erase that. So it's okay. So you can sort of see this spin here is in the same direction, right? This spin here is now facing you, right? This spin here is facing the opposite direction. This spin's facing away from you, and this spin is facing away from the spin. So if you look at these spins, if you just draw arrows, you might think that, okay, it's like this, 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 this. Okay. So the key concept now is that just by turning on this gradient and allowing the spins to process, I'm getting, and I take a snapshot after some point in time, the phase of these spins has a certain orientation, certain relative relationship, right? So what would be what would you say if I just showed you those were the spin orientations, what is the period of that variation? Assume that this has a distance of 1. What would you say the period of this spatial variation is? So how long does it take to go from a spin pointing in the same direction, in one direction, to go back to that same direction? How many steps does it take? Go ahead. 4, yeah. So the period is 4 here. Okay, so that's a key. When we're talking about period, we're saying what distance does it take for a spin? If I see a spin pointing this way, how long do I have to wait before I see another spin pointing the same direction? And that's the period. So that's a spatial period of 4 here. Okay. Now I take another time step, and each person does the same thing again. You know, the person in the middle stays the same. The person in front of them goes 90 degrees counterclockwise again, and so on and so forth. So now you sort of see this person is still in the same position. This person now is facing this direction. This person is facing this direction. This person is facing this direction, and this person is facing that direction. Okay. So now what is the period of spatial variation? How long does it, how far do I have to go before the spin orientation repeats itself? Yes? How about you? In the middle here. You took the last one. Yes, go ahead. 4? Okay. So but it was 4 previously. So this had a period of 4, right? So you're saying this right now is still a period of 4. Okay. And there's another suggestion in the back. 2. Okay. So the other option is it's 2, right? And 2, it is 2 because if you go from here to here, that has the same orientation. Okay. So when you're looking at these spin, so in some of the homeworks and exercises, you'll be looking at these spin orientations. And so it is good to realize that what you're looking for is when does a spin orientation repeat? What's the repetition of that spin orientation? Okay, so you can always look at, okay, if the spins are pointing at theta equals 0, how far do I have to wait before I see another theta equals 0? And that's the period. Okay. And if I play this game again, then here I get this pointing this way. Now it's pointing this way, this way, this way, this way. So what is this period? Okay. Yeah. Are you saying? Okay. Go ahead. 5. Okay. Let's think about that. So from here to here it repeats, right? So that spacing is close to 5. It's 4, right? So 1, 2, 3, 4, right? So that distance is 4. Okay, so the period here is 4, which is exactly what we got here. What's different between this row and this row? What's different about the spin orientation between those 2 rows? Yeah, in one case, it's what you're going to do in your homework. And the direction of helix is different, right? Because here, this person's facing away from you, and this person's facing towards you, right? So if you thought about the overall direction, so one is a positive frequency, one's a negative frequency. Okay, that's all we mean by positive and negative frequencies. It's just what's the handedness of the rotation. Okay. And in this exercise, if we did one more step, then they all return back to the same position again. Okay. And so in this case, there's no variation here. Okay. So what we're going to say is, in terms of spatial frequency, we're going to say this has kx equals 0. It has 0 spatial frequency. Okay. This one is going to have kx equals 1/4 because 1 over the period is 1/4. This is going to have kx equals 1/2. Okay. And this, and here the signs may be off, but this will maybe have kx equals minus 1/4, x equals 0. We'll have to think about the signs, but at least the numbers are correct. So that's basically how you go from the period to the spatial frequency, right? So spatial frequency is 1 over the spatial period. So when you see anything like this, you basically can always just look and say, okay, what's the spatial period of my repetition? And 1 over that's just my spatial frequency. Right? Okay, so that's just shown here. I think we don't have to go over this. This is sort of the same thing, just sort of a bird's eye view. Okay, it's like if you're looking down on people. And so now we want to sort of get this into phasors because we want to start working up to how is this going to do our Fourier transform for us. Okay. So remember, the Fourier transform of any function g of x is just e to the minus j 2 pi kx x multiplied by a function g of x, and then integrating all that. Okay. So look, this term here is just theta equals minus 2 pi kx x. Okay, so what does that term look like? Well, let's say, and for all these, we'll assume that kx equals 1. So at x equals 0, 2 pi kx x is just equal to 0. So that means theta is just equal to 0. At x equals 4, 2 pi kx x equals pi over 2. But I have theta equals minus that. So theta is equal to minus pi over 2. So we're just sort of mapping out what this phasor looks like. Here we have x equals a half, so 2 pi kx x equals pi. So here's theta equals pi, okay, or minus pi. It doesn't really matter in this case. And here we have 2 pi kx x equals 3 pi over 4, which would go all the way around here, right? So that's theta equals minus 3 pi over 4. But that's the same as theta equals pi over 2. So what we're seeing is that this term that we need in our Fourier transforms is just some time spatially varying phasor. Okay. So it's, and we just saw that if you had spins in the presence of a gradient, you could get a spatially varying phasor. So we were sort of seeing, oh, actually, if we can just impose these phasor patterns on our object, maybe we can get what we need for a Fourier transform. Okay, so let's take a look at that. So remember we had at kx equals 0, right? Then if we plug that into our term, it's exponential minus j2 pi. This is the kx term, that's 0. So this just is 0 phase everywhere. So you see they're all pointing in the same direction, right? So that's kx equals 0 is just no spatial variation of the phases. Now let's take kx equals 1 over 8 delta x. So that means that my spatial period is 8 delta x, right? We're assuming this distance is delta x. So let's do a sanity check on this. So the spatial, from here to here, that distance is 4 delta x, right? But from here to here, have I gone one period? No, I've only gone half a period, right? Because this is pointing this way, and this is pointing the other way. So that means that a full period must be 8 delta x. So that I at least got this 8 delta x correct. And if you see that, I can plug this in. I have e to the minus j2 pi. I plug this in. So it's 0, the phase is always 0. And here, as a function of x, it's going to be more clockwise in the positive x direction, and then counterclockwise in the negative x direction. And you can sort of see here that over this distance, it's just half a period of variation. And now I go here, so 2 over 8 delta x, which is equal to 1 over 4 delta x, right? And so now here I see this spin here and this spin here have the same orientation, right? And they're spaced apart by 4 delta x. So the spatial period there is 4 delta x, so that makes sense that kx equals 1 over 4 delta x. And so here, if you look here, this spin here has gone clockwise that way. This spin here has gone counterclockwise that way. And this has gone all the way this way, and this has gone all the way that way. All right. So just trying to sort of help motivate the fact that if you have spins in the presence of a linear gradient, you can get these phasor patterns that are essentially just going to be the basis functions for your Fourier transform. Okay, so now we're going to spend about 5 minutes. So we'll just review a little bit about how to think about Fourier transforms, and then we'll pick up next time and go into more depth. So just to remind everyone, you know, this is really key. Basically, this is what we want to try to implement with MRI. We want to figure out how we can get the Fourier transform of our object. So I have some object. I'm going to use the gradients to create this term. And I'm going to integrate over all that with our RF coil. And I'm going to get the Fourier transform at these different points in kx and ky. Okay. And then once I have that, then I can take the inverse Fourier transform and get my image back. And so that's the game plan. How do we start making our MRI acquisition look like a Fourier transform? So what we have to do is we have to review this concept of K-space. So K-space is just Fourier space. But if you do MR, you'll hear the term K-space all over the place. So you just have to get used to the term K-space. All right. And just to remind you what K-space is made up of components where at every location ky, we're just representing a complex phasor, e to the j 2 pi kxx plus kyy, which from Euler's theorem we can write as a cosine plus j times a sine term. Okay. So let's just look at this cosine term, right? Let's just forget about this for now. Let's look at this cosine term. Let's say ky equals 0, right? Ky equals 0 means I'm not going to have, cosine has no dependence on y, right? Because this term is just going to go away, right? So if you ever see ky equals 0, you know, oh, there should be no dependence on y, right? All the dependence has to be on x, because I'm just going to have something cosine 2 pi kxx. That's the only term I have left. So I'm going to end up something like a wave pattern that just varies along the x direction. That's all kx means, all right? Similarly, if I made kx equals 0, now I only have stuff that depends on y. So I should have no variation in the x direction. All the variation has to be in the y direction, right? But I can always have both of them, kx and ky, which just means that it's got to vary both in x direction and the y direction. Okay. So in general, I'm going to need all sorts of all these patterns. So I'm going to construct my image out of different patterns at different spatial frequencies and different orientations. So useful thing to know is that if you're at any point kx, ky, okay, then this angle is just arctangent ky, kx. Okay. And it represents a spatial frequency that has peaks like that. So what that means is if I give you some point in kx, ky, like this, to know what that looks like in image space, you just have to draw an arrow at that point. And then you draw the perpendicular to that, that's the pattern that point in Fourier space represents. Yeah. And as we talked about, the other really important thing is the center of K-space. Okay, so you'll hear about, we're going to talk about center of K-space, we're going to talk about inner K-space and outer K-space. Okay. And it's going to be important for you to understand what those mean. And so as we said before, the center of K-space is just the value of the Fourier transform at 0, right? And that's just the area of my image or my object. So all it says is that if I look at the center of K-space, for most objects, like if you look at a human brain or a stomach or a liver, there's going to be some overall, level, the average sort of proton density in that is the area of my object, right? And so in general, the center of K-space is always going to be the strongest thing, right? Because that's sort of, there's something there, you're going to have something at the center of K-space. When everything else is variations around that. Okay. Oops, that's not what I meant to do. Okay, so let's look at an example. So this is the Fourier transform of someone's brain, and you can sort of see the center of K-space is pretty bright, and it sort of dies off as you go away from the center of K-space. So the parts that are bright, that's like the inner part of K-space, and then as you go out into outer parts of K-space, there's less information out there. So if I pick a point here on the Kx, some along the Kx axis, and I say, okay, what does that point in K-space correspond to? Well, we just said that it corresponds to variations that only vary in the x direction. So it would look like some variation here. Okay. And then if we go farther out along the Kx axis, then that's at a higher spatial frequency, right? So the spatial period has to be smaller, and that's going to correspond to something like this. Okay. And then I can go off here along the Ky axis, and it corresponds to something that only varies in y. And then I can go out farther along there, and this sort of the spatial period is decreasing. So the farther out I go in K-space, the smaller that spatial period has to be. Okay. And then if I go out here along some direction in Kx, Ky, remember if I just drew something out here and drew the perpendicular, it would be sort of pattern that's perpendicular to that line. And so that's this line here. All right. So we'll have to end there. So are there any questions before we sign off? Okay, so if there's no questions, we'll pick up again on Wednesday. So see you then. And I'll stick around here if there's questions.